Nu is het beter dat ze niet meer komt, want anders gaat ze... Nu is het beter dat ze niet meer komt. Ik ga gewoon uitleggen.
Which one?
It's this one.
Oh, this one.
No, no, this the other one. This one. That's the one with the borders of it.
It's okay.
Yeah,
This one. Let's see.
What it is. Yeah. Just, I don't need to put the microphone.
CC. Yes, yes.
That
Got
really-
it. It's only for the
Yeah,
chips.
That's fine, I'll do it.
And but the problem with my mouth.
No, it's good. I'll do it.
So, can we start the next session about the technical part? First speaker will be Kat.
Hello, everyone. First, I'll wait a bit. So first of all, I need to apologize because my colleague who was supposed to present, I also had a presentation on her laptop, had a problem with the train and she's still traveling. So I took over. I just got the presentation 5 minutes ago and I changed it a bit. So I apologize for the small mistakes I might make, but I know the research, so it shouldn't be a problem. I will be brief because this session is on the powered ankle foot orthosis and then the following one is on the hip module. So the only thing that I do is give you an introduction why we need such modules and how this was developed. Just briefly, as you know, cerebral palsy is the most frequently observed motor disability in children. It's caused by a non-progressive lesion in the brain and it's causing symptoms like muscle weakness and spasticity. And these are primarily found in, for example, weakness is mainly found in the soleus and in the hip muscles, the hip extensors, so the ankle muscles. And these two muscles are very important to keep you upright. Spasticity is observed in other muscles, like gastrocnemius, medial hamstrings, and so on. Due to the growth of the child and the continuous impact of these symptoms, you get secondary deformities like bone deformities and muscle contractures. So I will first introduce the powered ankle foot orthosis, and that will be the largest part because there we made the most progress and that will be presented then afterwards by our colleague engineers. But in order to do that, you need to be familiar with the 3 ankle rockers. 3 ankle rockers means that you have, if you describe the ankle motion, you can do that in 3 different parts, 3 rotations. The first one is a rotation around the heel. The second one is the rotation of the tibia, the forward progression of the tibia during stance. And the third one, which is a very important one, is the push-off. That's the rotation around the toes. You need to know these 3 rockers, otherwise you will not understand how the powered ankle foot orthosis has been developed by the engineers. This is then to indicate that it's a bit more complex than that, because you have 3 rockers, but in the rockers you also have subphases. And if we want to control an ankle foot orthosis with the motor system, we need to know when the motor system needs to be working. So that's why we need to be familiar with these events, and we should also be able to detect events, these events such as the motor can give power at the right moment. But first of all, why do we need this? As you all know, children with cerebral palsy have ankle foot orthosis. That's a very common clinical treatment. And this is used to prevent secondary deformities, to improve the gait pattern, and also give good balance, and so on. It's more a preventative treatment. However, there are some benefits and harms in the ankle foot orthosis. It's not all good what is. There she is. I'll continue. So just for those of you who are less familiar with children with cerebral palsy, this is a child with cerebral palsy who was walking. Anyway, what I wanted to say is that children with cerebral palsy they are very different. They are very heterogeneous. You have all different gait patterns. And here you see an example of a gait classifications that has been developed in our research group. And Laura also did a lot of studies on this. And it's also good to know that a child who's, for example, walking in a crouch, in a flexed pattern, will need other orthosis than a child with a genu recurvatum, a hyperextension pattern. The other thing is that not everything is good in a child with with an ankle foot orthosis. And one of the things that do not properly work is this third ankle rocker. This was all supposed to be a movie, but it doesn't run. But it means that the push-off phase is really something that doesn't work in the ankle foot orthosis. The rest is pretty good. So if you summarize, initial contact with the conventional ankle orthosis is quite good. During mid stance and terminal stance, the control of the tibia is more or less okay. So we do different things for children who are walking in crouch and different things who are working for children who are walking in hyperextension. You just tell me if you wanted to say something else. And then it really is not good for the push-off. And then during swing phase, it works pretty well. So the powered ankle foot orthosis needs to focus on this central part. And we zoomed in on that. So what will be explained later on is it will do more or less in swing phase and at initial contact, more or less what a conventional orthosis is doing. However, the powered ankle foot orthosis is more clever at initial contact as well and during loading response. But it will especially do something in the second ankle rocker. Try to control that. And there we need to do different things if a child is walking in crouch or when they walk in hyperextension. And the most important thing is that it will also help the push-off, because all patients who have an ankle foot orthosis, all studies highlight that the ankle foot orthosis is really preventing a good push-off. So if we can help them in the second and the third ankle rocker, it will be a big improvement. Just to show you here that the child is walking with crouch and to make it more concrete, if they walk with orthosis, you see that you get them out of the crouch at some point. It's not running very fluently, but it's just to give you an idea, but you will see other movies later on. So this was the introduction for the powered ankle foot orthosis. After this presentation where the engineers will present what has been developed and tested, there will be also a presentation on the hip module. I don't see. Yeah. And this is also to introduce you why this is done. So if you look at the child when in crouch, well, with an ankle foot orthosis or with a powered ankle foot orthosis, we might be able to influence the knee joint and then through the knee joint also, the ankle joint. And through the ankle joint, we can also influence the knee joint, but it's very challenging to also influence the hip joint with an ankle foot orthosis. But children with CP do have major problems at the hip. They have spasticity, of course, but in lots of children, you have a lot of weakness in the hip extensors. So that's why they get into crouch. So there are actually no hip orthoses that can control that in a proper way. And this was the trigger for the hip module. But then Luc or Sander will give more details about that. So thank you. I think now
perhaps also a good idea.
Yeah, it was nice.
I just need to get this presentation out. Shall I just pull it out? Yeah. Yeah, thanks. Oh, the microphone.
Yes, yes. Is the presentation?
Okay.
Yes. The font is unknown. That's why it looks different. But it is the good one. Hopefully because it runs on a different. Yeah. Yes. Still need the microphone. Huh?
Yes, you need to make.
Okay. I will talk a little bit about the technical development of the PAFO. And since it is Friday the 13th, I also noticed, because it's another computer, that the font is not on this computer installed. So I hope that the formatting will still be fine. And so you have quite some nerve organizing it on the day of bad luck, Friday the 13th. And we will also have live demo, so might be a bit, we will see. So Kat already stressed like pretty severely that timing is quite important whenever you control human motion. So that's why all this timing stuff is quite a big block in the total algorithm. And if we can work out the timing, we can make a sort of classifier that does things to the PAFO in each time step. And then sooner or later, you will need some hardware. One piece of hardware is actually sensors that measure something about the movement. And another part is some kind of actuator that actually applies forces to a person in this case. And you also should transfer those forces comfortably. So we will also be in need of a custom developed AFO. So this is like a global scheme of all the problems we need to tackle to build a successful PAFO. So if you look at this gate event detection, it's the biggest part, of course. It will take some sensors, some data from the real world, and do some software. And basically all in the red box is software, and everything outside of it is hardware, so that goes to the real world. And if you would check the literature, come in, welcome. There are quite some complex systems, and oftentimes they use sensors inside of the shoes, and that's something that we don't really like because the cables there, they wiggle around with every time step or every step, so they're prone to mechanical failure. So luckily there was a publication by presumably a very nice guy called Bekpoldi in 2019 who solves this problem and is able to detect all the phases that Kat presented, so the full, not only the rockers, but the full 7, with 2 gyroscopes on the shank. So no more these cables inside the shoe. And also the algorithm is quite simple. It just looks for 0 crossings, minima and maxima. And these are inputted into a finite state machine, which is a fancy name of saying you have a certain set of conditions and there is a certain set of rules to transition in between those conditions. So since gate is cyclical, or most of the time, you go from bit stand to terminal stand and so on, and the program knows this and allows you only to do this. In case it goes wrong, we implemented a init state where it just waits for the next step. So, this slide is a duplicate of what Kat already mentioned, so I'll just go on. A gyroscope is a fairly small sensor. That's the second advantage. But if you want to couple it with some microcontroller for the readout and you need some user interface and logging capabilities, then it becomes quite a device. But this is how it looks on the child of Louisa. I don't remember anymore, 6 or 7 or 8. 7 then. So still quite fine. Although I should say that now we use some different gyroscopes that run with our actuator. They are flatter, but a little bit bigger. Don't panic now. If the classification is successful, you will hopefully see it on the live demo in the afternoon, you will see all these colors. And basically these colors represent the steps like the loading response, bit stands, terminal stands, and so on. This works okay, but the disadvantage of an algorithm that is so simple is that it also sometimes triggers. You would say that this transition should be more towards here. But here's a little bit of a noise pattern, so it triggers a little bit too early. So we implemented, how would you call it? A sort of numbers that actually knows when it detected the first time and then waits a certain amount of samples. So you can fine tune this to have it on this, more or less a hit or miss. So also perhaps good to stress that these are milliseconds. So the question is, will you really feel if it's 1 millisecond before or 1 millisecond after? But since I stress here accuracy, you might also say how accurate is it? And we have a limited data set where we actually reference this in the GateLab. And it's quite accurate, at least to my standards. Like the initial contact we can detect in like 12 milliseconds from the force plate data, and the same for the opposite initial contact, which is basically the same but the other foot. The toe off is like 50 milliseconds, and then the heel off, that's a bit of not such a good detection, that goes to 160 milliseconds. So there we are a bit in the blue. But still, and it's also important, this is for a healthy subject. So we should still do this for a CP child, but measurements are trickling in like not very fast. And I also mentioned this perhaps already. If something goes wrong or the algorithm stays too long in one state, we actually time how long it was and how long you expect it. And you have all parameters for this. Oh, hello, come. And it goes then in an idle state. And there you can choose what the AFO is. In this case, it plays a transparent AFO, so it will not supply any power. You can also set it up that it plays a stiff AFO in this idle state. And it will just wait for the next step and then continue to provide power to the user. Then we have something, hopefully you believe me that it works more or less okay. So the next thing is that we need a motor that actually provides power to the user. And we have kind of a special motor. Well, it's not so special, but kind of special. Normally you have an electric motor. It's a brushless DC motor. There's some gearbox to make the speed go down and the force go up. And then there's a spring in this motor. And perhaps you can go back to your physics lessons of some years ago. If you know something about the spring and you measure its deflection, you can also work out the force that's acting on it. It's actually a quite nice thing. And secondly, because there is a real spring in there, like walking is like impacting with the ground with every step. And if there is nothing to buffer this impact, those poor little teeth in the gears here, they would suffer quite a bit. So that would also increase the longevity of this device. And we went for a commercial one. The choice was very limited. We found two, and we then bought this one. It's called a Hebi X89 from Hebi Robotics. It's not just the motor, the gear train, the spring, the driver, the communication module, it's all in here. And it's like almost 500 grams in this little block. That's the best we could find and do. And here you see an example. Do we have sound? Ah, yeah. You can hear now the sound pitches. Now the motor starts in a timely manner. This you will hear also later, so you can listen to the sound and see if we are cheating, yes or no. And also in this example, you saw that the motor was actually on the shank. And it's not the only thing that was on the shank. There are also lots of other mechanical components. So the weight of an adult AFO with the module on the shank combined to 1.4 kilos, which for an adult was quite fine. But for a child with muscle weaknesses, it's just unacceptable. So we had to search for another solution. But still, from an engineering perspective, this still makes sense. Eh? You want to minimize all kinds of trouble in the first stage. When everything works, you move on to make it better for the target group. And we found a push-pull cable, which, as the name suggests, you can push and pull with one cable. I think many others use Bowden cables. We also used them in the past, but we found it troublesome to remove all the slack. So this is a more easy solution, but they're also quite a bit stiffer. This might also interfere with the, the gate pattern. And also this allows us now to place all the heavy components in a backpack solution. And here you see only the two motors, and then there's a convenient wire running off to the batteries and so forth. But in the current setup, we have all of this in the backpack, which means two of these motors. There's a battery in there that supplies 36 volts at 3 amps. There are some inputs for safety switches. So there are two emergency stops, and also the user can have a deadman switch is the name. So whenever he releases the button or presses too hard, the device will stop. There are connections to go to the I/O cards, and also there is an Ethernet switch inside to distribute the Ethernet connectivity. Total weight of this backpack as it is now, with the cover included, is like 4.3 kilos, which is still quite hefty, but it has a bunch of metal in it, so it's not really much we can do. Carbon fiber was used to make it as light as possible, and fully with the AFOs attached, with all the cabling and so forth, it amounted to 6 kilograms in total. And if you place this on an adult subject, it looks quite fine. I wouldn't say very nice, but quite fine anyway. We also tested this with a healthy subject of 12 years old, still looks quite fine and acceptable. And then we also tested on a 9-year-old child, and I think that is, that's becoming like the lower limit of what is feasible. And now also, I think 2 weeks ago, we were a bit in panic because a child of 6 years would be recruited for this. So that will never work. And also it was more severe, so it would probably collapse under the weight. So we also devised a solution now, with something I borrowed from photography, where you can just place the backpack on the treadmill and you will have longer cables going to the leg. So it's actually no weight anymore to the back of the children, which is probably a good idea for the 6-year-old. Then perhaps the thing I like the most about this project, sadly I didn't develop it, it's from other intelligent people, is the customization of this Afro brace. So if you would have a brace that turns and is also on your leg, the axis of your ankle and the mechanical one of this should be pretty good aligned, or you get shear shifts. And my colleagues here developed an algorithm where you can start from a 3D scan and all these hinges. So the 3D scan and the algorithm, they detect the actual ankle axis and align all these joints. They generate the mounting points for the push-pull cables, for the I/O cards and so forth. And out of it comes an STL file that you can ship to any 3D printer company. It comes back to you at 5 days. It's quite nice. So I think I covered now all the mechanical steps. Now the question is, how do we actually control this thing? And we do this not with a fixed trajectory. So we don't give a fixed time point in every step where you get this fixed walking pattern. We use kind of a virtual spring mechanism, which basically means at every time step, the 7 phases of gait, you can give the controller a target position and a certain stiffness. And if the difference in between where we want to go and where we actually are is large, you will feel a good and great amount of force. But the more you get to your target position, for example, in the swing phase, your foot gets lifted up, the less you will feel the interaction. So actually the user is more or less free to move around this 0 point. It's only when he deviates a lot that he will feel the force pushing him back. So this allows a natural walking pattern with slight deviations in every step. And actually, you have set points for each of these steps. And we invented 2 more, so we actually have 9 time points where we can interact with the user. As of now, we have measured 2 adult healthy subjects, 2 children healthy subjects. The first CP child of 15 years old is measured and the data is being processed. So it's a heavy job. And I think there are 4 more in the running, or 3 currently, with their AFOs being casted. So this will be fairly soon that we know a little bit more. I think that was all that I had to say. Sander, please. Oh, Luc, sorry. Ja, dat wist ik niet. Ja. Ja, dat heb ik. Sorry? Sorry, I stole the mic.
Okay. Thank you, Laurent. Yes, well, I wasn't present during the presentation of Laura about the clinical aspects, so maybe I will repeat some of these things, but I will try to do my best to keep it short. At the same time, I heard what Roy was explaining. I will discuss a little bit about the hip module that we developed and built at KU Leuven. In the lab also in Geel, so very close to MobileUp. And in fact, I will probably repeat a couple of things that Roy has also been explaining already to quite a nice extent. So probably easy to understand that we will do very similar things with the hip module as what has been done with the PAFO, in fact. The majority of the work has been done by Sander, so he deserves all the credit for the work that has been done on this hip module. We wanted to have a separate module for the hip joint rather than building a full exoskeleton at once. to be later combined also with the ankle module maybe, or with the full exoskeleton that was developed in Lille. But there may be some benefit for some patients when only the hip joint is assisted. So that's the reason why we think that it makes sense to have this kind of device separately. And the reason for it, and maybe you have seen the graph, but if you look at the gait and particularly at the joint angle at the hip of CP children, like crouch gait and apparent equinus, it's very clear if you compare it with the typically developing children, the blue curve here, that these children also sometimes show more flexion overall in the gait pattern, and this is probably due, or in some cases at least, due to weakness in the gluteus muscle. And that's why we think it may be beneficial for these patients to add some or to assist somewhat in extending the hip joint, particularly during stance phase. And so that's why we came up with the idea to devise a kind of hip module for these patients, where we have an actuated degree of freedom, which is the hip flexion and extension at both sides, of course, of the patient. And then, of course, the other degrees of freedom that you have in your hip joint, like rotation and also ab and adduction, should be kept free, of course. So people can move in whatever fashion they like in that sense, but we only look, or we only add some flexion or extension torque. The torque control, we can look at it from different levels. You have a low-level control in this kind of devices, of course, and as well as a high-level control. The high-level control, I will come back to that in a minute, and also the low-level control, I will say a little bit about this. And then, of course, you have to put it on the patient. You have to devise custom-made cuffs to bring the extension or flexion torque from the module or from the actuator on the body of the patient. And for that, in this case, we need, of course, a trunk module, a custom-made cuff for the trunk or a corset for the trunk, and also something which puts it on the upper leg below the hip, of course. It looks, the design that we made looks a little bit like this one that you see here, which we took from an article, but there are some different features on it, and we made quite some better things about this device. So, but it looks quite similar, in fact. So this is the topology that we came up with at the end. Again, it's a SEA, so it's a series elastic actuator that we use, not just a motor, but a motor combined with a spring. In our case, it's a torsional spring, not a linear spring. We made our life, or particularly Sander's life, quite a lot more difficult, because we didn't choose a device where you have an actuator with a spring included and with all the control and everything included. So Sander devised his own spring and devised also the full control algorithm of this actuator, in fact. So these are the two actuators with the springs on top of them. You have this freedom for up and adduction. You have the two cuffs for the upper leg. You have the corset for the trunk. The electronics should go on the back as well, just like in the PAFO, of course. And we are using as high-level control also these two IMUs. So we measure at the lower leg the rotation, the kinematics of the lower leg, in fact, to discriminate between different phases in the gait, just like Mobilab does. And in fact, we are using exactly the same algorithm that Mobilab also designed. But now, of course, we use the information from these IMUs to control our hip actuators. And again, for safety, we have a deadman switch. You will see it when you come to the demo. And we have also another just emergency button as well. So we can, as soon as something goes wrong, either the patient or the physiotherapist or the engineer who is sitting next to it can push those buttons and the whole system will shut down immediately. And it will, it will not provide any torque anymore. So you will not feel anything, although the voltage will still be on the device. There are a couple of slides that I will show you. I'm not going to go into detail because they are very technical. And Sander can explain much better than I can do. So if you have any questions about those, please come to us at the demo. First of all, the SEA designed actuators themselves, you have to find a motor which is capable of providing the right torque at the right speeds during walking, and it's not that easy because walking is a highly dynamic way of behaving. So these motors, well, there are not a lot of them available, and to find the right motor is not just a matter of looking at what is the maximum torque or what is the maximum speed that we need. You have to look at the full domain of the thing. So we took everything into account. There are some algorithms to do this kind of sizing and dimensioning of these actuators. You need a lot of mathematics, in fact, to do that. Fortunately, we got some information of both patients and healthy subjects from the people in the gait lab of Pellenberg at KU Leuven, where we could find typical gait patterns, both of patients and healthy children of the same age group that we are looking at. And based on this data, as well as the data from the motor, Sander was then able to look at, first of all, the transmission, the proper transmission that we need with a transmission ratio. We chose for a transmission ratio of 81 in this case. So the motor torque is multiplied by 81 and the motor speed is divided by 81 to reach the right torque and speed targets. And by choosing this transmission ratio, you can see you can probably accommodate all the patterns of gait of all these children which are in the database, both the patients and the typically developing children. So that was one thing that we needed to do. Next to that, we needed to design the spring, of course, to convert or to transmit the motor torque to the hip joint. Again, you want to do that in the most efficient possible way. You don't want to lose too much power. You don't want to lose too much torque over the entire dynamic range of gait. So again, that's quite a lot of mathematics to be done. But in the end, we were able to design a spring with a spring ratio that was accommodating all this data, and which was also as light as possible, because the weight of the whole device, of course, needs to be taken into account. You have heard that from Roy as well. Sander made some nice finite element modeling to check whether the design of the spring was okay and whether it would give the right spring ratio. And after manufacturing it, we also measured it on our in vitro setup, and it looked like it was quite comparable to what we envisioned in the beginning. The control, I'm not going to say too much about it. We are using the same algorithm as what Mobilab is using. But in our case, of course, we made it a little bit more simple because also it wasn't very clear to us exactly what is needed on a patient. So you can go for impedance control, of course, so making a virtual spring. We could do that with our device as well. But then it's not, an ankle is behaving more or less like a spring. If you look at normal gait, then you can find a slope in the torque rotation graph of a typically developing child. So that slope gives you then the spring stiffness that you need. Also in a PAFO, for instance. In the hip, it's not that clear, so it's not so easy to simulate a hip with a virtual spring. So that's the reason why we made it a little bit more simple, although the device can do many more things, and also the control algorithm that was designed can do whatever you like. Basically, it can be used as an assistive device, but it could also be used as a resistive device, maybe to train patients if that is necessary. Right now, we are just applying a fixed torque level starting from mid-stance until the end of the stance phase. And as soon as the child goes into the swing phase, which is detected by the IMU, the device goes into a transparent mode or can apply a little bit of flexion torque, for instance, to help assist the swing phase. But we can do many other things as well if needed, and depending, of course, on the input that we will get from revalidation people and from patients themselves, of course, as well, to maybe tune it. And maybe we can look for algorithms which are more applicable in apparent equinus or in algorithms which are more beneficial for crouch gait people, for instance. So there may be differences between different patients, and it's quite possible and relatively easy with the existing algorithm that we have now to implement these different kinds of control algorithms at a higher level. But right now we kept it simple, and we are going to test it as soon as possible, of course, in the patients and find out what is the best thing to do. That's what it looks like now. The mechanical interface, again, well, since we can apply quite a lot of torque at the level of the hip, we need quite a lot of stability, and the cuffs need to be fixed to the body quite tightly. That's the reason why we have to make them custom made. Apart from the upper legs, maybe that's not that important, but certainly this one should be fitting really tightly on the upper body. Right now it's still open at the front, but we have experienced during measurements with Koen here that we in fact need some extra support at the level of the sternum to apply extension torque at the hip. Certainly when we apply larger torques, that's going to be necessary. You see here as well the actuator. Here you see the up and adduction hinge, which is making it free to move. You see also a relatively heavy rail here, which is fixed to the cuff on the upper leg. And this rail is needed because, in fact, our up and adduction joint hinge here is outside of the hip joint. So when you perform up and adduction motion and the device is connected here, this will lead to some movement up and down. And if we would fix the rod here tight to the cuff, then you would experience the cuff sliding over your upper leg, which would be quite annoying and probably even painful. So by having this rail, we avoid this kind of movement. Also, what is very important, and again, where MobileUp helped us quite a lot, is the design of this corset and making sure that the alignment of these actuators is really exactly at the level of the hip joint. As soon as you are a little bit off, this will again lead to unwanted and uncomfortable movement of the device. So you should really, and certainly if you're talking about patients where there may be some anatomical deformities, for instance, it's important to be able to put the actuator at the right level, starting from external landmarks. So that's what Daniel has been doing. So I should give the credit to the people here as well for the design of this corset of our device. And this is, you will see the device later on, of course, during the demo. So we can do overground walking as well. We tested it out first with walking on the treadmill. And you can see, well, it's a little bit too short. Maybe you should have a look at it, but you can really see the thing going up and down along the rail at the back. If you look at it carefully, you can also see when we apply torque, this was in transparent mode, but when we apply torque, that you can see the spring extend and compress again. So you will be able to see whether it is really assisting. Otherwise, there is not much to see about it because it's not really clearly visible whether you are assisting or walking in transparent mode. You can only see it. Well, the person who is wearing it can feel it, of course, but you can only see it as an observer when you're looking at the spring. We can go up to 50 Newton meters at a peak, 35. Okay, yeah. Yeah, so it's quite, yeah, okay. So it's capable of applying quite a lot of torque. It's this, yeah, we asked Koen to walk in crouch gait, and when we applied full torque, it became difficult for him to put his hip into flexion, even during the stance phase. Yeah, that's why we need the sternum support. Yeah. I should say one more thing. The weight of the whole thing is 8.5 kilograms right now. So that's a lot of weight. There are some possibilities to lose weight when we are developing more prototypes or next generations of the device. We'd rather limit the weight at the rails, for instance, and at the other hardware rather than at the level of the motors, because we think we need the power of the motors really. And as soon as you take away weight from the motors, you also drastically reduce their power and torque outcome. So that's something we would maybe consider doing if we find out later on that we don't need the full power. But right now we prefer doing some weight reductions at other levels, at the electronics, for instance, as well. That's also a possibility. That's it. I hope it was clear.
Another presentation of the lower limb part. Presentation. The speaker is young.
Sorry, we have some late updates on the site. So here I want to present some some development on the lower limb part. So this presentation gonna be made by us from Junior HEI, and also some development at the University of Kent, which will presented by Mohammed, and also something about the clinical usability test planning of the St. Martin Clinic. So let's first hear the small contents of what we have. So that's first, of course, the development at HEI. So we have named our exoskeleton as Ines, at the name of the children of Luke, and we are talking about some mechanical part and control part, and also the user interface, and also the test of our faces with healthy adults. So here is as you already show a lot of video. Here we have little logo for our exoskeleton, and here is a prototype. And we have not like the other prototype, we have a full structure and also with multiple motors, actuation units. So that's make our exoskeleton, our prototype, the heaviest design among the three prototype. So we have mostly for the hip joint, we have two actuated joints for abduction, adduction, and also for the flexion and extension, and also for the knee extension and flexion. So now we didn't design we don't have actuation units on ankle joints, but we found that actually it's quite important the actuation units on the exoskeleton. So maybe in the future we will integrate the part of MobiLab to the full lower limb exoskeleton to make a whole fully actuated structure. That would be very nice, I think. And also the motors now we are using, it's just conventional design with a gearbox and DC motors without springs. And it would be also nice to add springs as a SIA structure to have let's say a more higher level control with force control with impedance control, some more sophisticated control algorithm. Because now for this design we can just doing position control. That means we have to impose a fixed trajectory to the exoskeleton, and there's the interaction between user and exoskeleton is not that much considered. We are more like force the patients to follow in certain gaits. So yeah, that's could be in the initial phase. That's how it works. And for the structure, we use we mainly use three types of materials. So it's aluminum, and carbon fibers for the tubes, and also some 3D printed, small accessory, let's say, for the exoskeleton to minimize the weight. And finally, we still got 20 kilogram weights for the total structure, and mostly come from the actuation units. Actually, I think each of them weigh like 1.6 kilogram, so that's lots. I hope we can in the future, maybe in the further version, we can modify this design, or there's some new techniques comes, we can benefit from these new techniques and have a more compact, lighter actuation unit. And and because it's not a customer design, we want this design to use for multiple ages. So there's some size adjustment structure mechanism, like the telescopic tubes. So the tubes we have a small tube and larger tube to connect together as a telescopic structure. So we can change the length of the limbs, and also on the back we can also change the length according to the width of the patients. When we design, we are focused on the children from 6 to 12 years old. And we also have, like the hip module designed by Sander, we also have some sort of alignment mechanism to allowing the hip internal and external rotation. Okay, so that's our actuation unit. So we use the Maxon EC motors, and also the harmonic drive, string wave gearing. So that's the most, I think, the most precise gearing in the market. And here is a final design with on the knee joint. And here is the power and the maximum torque we can produce for each unit. So for the hip joints, we can go to a maximum torque of 110 Newton meters. And for the knee, we can sort of 70 Newton meters for the maximum torque. And for position control, we also added a magnetic absolute encoder. Yes, here in the output shaft of the actuation unit. And here we have a full control architecture for our design. So we have our main controller, which is a SpeedGoat real-time target machine. So I think Sander also use the same controller. So this controller is can be served at the EtherGAT masters, because all the actuation units are communicate through EtherGAT protocol. And we also have another advantage of this SpeedGoat target machine is like we can program the control algorithm in MATLAB Simulink. So that's way much easier than programming in C++ or other control algorithms. So we can just drag blocks and program the algorithm you want. And because it runs in EtherGAT network, it have a very high communication frequency, up to 1000 hertz. We also have sensors. Unfortunately, these sensors are designed by ourselves, so we don't have the communication protocol in EtherGAT. So we use CAN bus. Actually, the CAN bus goes through this green line to another electronic box on the back of the exoskeleton. Then there's a shield, EtherGAT shield, to convert the signals to EtherGAT, and then it can go to the SpeedGoat as to receive the feedback, the sensor data from the sensors. And we also have a touch screen, which is STM32 based touch screen, to have a more direct user interface on exoskeleton itself. Here we also change the the protocol to EtherCAT, so that we can send the commands to the EtherMaster through this touch screen. And for the control algorithm, we have designed an algorithm based on the center of mass shifting, and also which is in state machine form. And we have also designed the algorithm for the automatic step triggering. So the reason we designed this algorithm is to, like, we found during the working, the transformation of the center of mass is rather important for the people being able to swing their leg forward. So our algorithm is basically in the state, like the state 2, we first transfer our mass on the future standing foot, and then we can start to swing the legs and push the patients forward. And so in each state, they are triggered by the actions like shifting weight and then moving forward. Okay, so we have the action A, the action 1, 3, 6. That's for the shifting weight, and we also another stuff we have developed is for the automatic step triggering. And the reason the theory behind that is like when we at first touch ground, we measure the ground reaction force, and after shifting weight on that foot, you measure again. You actually, it's a continuous detection of that ground reaction force, and we sense, that's reaction force. Evidently, it will be increased, and when it's increased to a certain threshold, that means your weight shifting is finished, and then you can start to swing your leg and move forward. So our algorithm is, as I said, we use MATLAB. We use a speedgo target machine. So the algorithm is programmed in MATLAB Simulink. So here we have a general. That's actually here you see just simple blocks, but under these blocks there are some very more complex algorithm inside. So we have a sort of first block for the EtherCAT network management. We have the second is STU part of the STU part for the algorithm. That's a like presetting phase of before you actually start the functioning of the exoskeleton. So in this phase, you can do some parameter tuning, like the PID parameter of the actuator. And we have the PDO algorithm. Actually, that's why that block is running in real time, and it's constantly constantly implementing your algorithm. So then that part we have embedded our control algorithm, like I showed before. So we also have developed two user interface. The first one is as we use MATLAB, another advantage is we can also develop some UI with there's a MATLAB application, a module that you can develop application inside, and this one can also call the MATLAB Simulink model to send some parameters to them, and also to get some streaming data from the Simulink real-time model. And with this, this is mainly for the development engineer or for the application engineer, so that they can tune the data, and also monitoring the functioning of your exoskeleton. You can see from these figures. And we also, because we have also a touch screen, and for the therapists, they don't need a very complicated stuff to continuously tuning your parameters. Actually, they should be presetted by the engineers, and for the therapists, they need a much more simpler user interface. You just click start and it will be working, and then you click end. That's all. So we have sort of this a very simple interface. We have some button inside, and we just click this button, and it will send the command to the it's got master, and we programmed some something inside, and it will react for this sending command. And yeah, we did some tests. Thanks for our colleagues here, our female colleagues with sort of small size, like so they are more similar to the children's, maybe not small little children, but children with a little bit higher, older children heights. So we have test with them. So here, I think, yeah, we have also already saw this video in the previous like Whitney's movies and the other movies. So here is our test. I think the most interesting part is finally we also tried to move without crutches. Yeah, but we still need the support behind them. Yeah. So as you can see, there's a certain weight shifting phase. So we shift the weight on the stand foot and then start to moving the three leg. Okay, I think that's all. So finally, I want to thank for all the people who have involved in our development and also the test. So thanks.
Okay, hello everyone. I'm presenting on behalf of the University of Kent. We are going to continue. We have some collaboration with Junior Hay regarding to the full lower limb exoskeleton, and we have some contribution in this technology. First of all, we have some initial research motivation about the cerebral palsy, and it is the most common type of neurological disorder, and about the different problems that this issue. And the most important thing that we are talking about here in terms of the problem for the cerebral palsy is that they have a 2 times or maybe more metabolic consumption in comparison to the healthy children. And the metabolic consumption, the problem is that is regarding to the weight. If we can reduce the weight or compensate the weight of the exoskeleton and the user, it can be very beneficial and reduce the energy consumption. In this case, we focus on the model-based control algorithm to compensate the gravity of the exoskeleton designed for children with CP. As much as the control, because the design is done, the mechanical design, only we have focused on the software to reduce the effect of the gravity. In this case, the model-based control and the gravity compensation control algorithm could be super beneficial to reduce the disc cage, and it could be helpful to make this design especially useful for cerebral palsy. We have a 2 design, first in terms of the mechanical illness that presented by Young, and it is the version Carol that we designed at the University of Kent. Similar structure, 6 degree of freedom at this design, but we have a different configuration for 2 degree of freedom, single leg lower limb exoskeleton, 4 degree of actuated degree of freedom that we are presenting in the next step, and 6 degree of freedom that you can see in this case that we have a hip in frontal, hip sagittal, and the knee. And another design that we are going to add the actuator for the ankle as well, that it will be 8 degree of freedom and it will be full lower limb exoskeleton that support whole of the joints. In the next step, we focus on the control, but first start with the control algorithm has a 3 step. The first one, the supervisory level controller that is designed with my colleague Rania, that she virtually joined at this meeting. In this case, we are going what we have done. In the supervisory level controller, the main goal is to drive the desired angle. In this case, we use the conventional neural network or AI based on the machine learning and the based on the deep learning to predict the one step ahead. This very helpful for us for predictive control. If we can if we have a prediction in terms of the gait for CP children, and it has some modification that you can see for healthy and for CP children, it can be very helpful for the high-level control algorithm because the control has a supervisory level, high level, and the low level. In the supervisory level, generate for us the desired trajectory that it is we modify angle. You can see here for healthy, it is very clear that it is in the right, the green one, and or design the algorithm that we are design follow the right trajectory. But here for the CP, the red one, it doesn't follow the red, but the algorithm that we apply can predict this one and make it exactly follow the trajectory. It is very helpful that the supervisory level controller has some prediction, can predict the next step for us, and in the right mode. It is very helpful. And the next step, we have a high-level controller. In the high-level controller, based on it directly depends on the low-level controller. If in the low-level controller, for example, we have a torque control, we have to use the high-level controller. The outcome should be torque. In this case, a robust impedance controller is the simplest one because we model the human-robot interaction based on the spring and the damper, virtual spring and damper. We drive the good collaboration, interaction between the robot and the exoskeleton, human and robot. And in this case, impedance control can be helpful. It's simple, but it should be robust. Why robust? Because it is not very accurate or model. There is some uncertainty, 30%, 40%, or maybe more and less. In this case, if we have a control algorithm, it should be robust. For example, robust tuned impedance controller, or we are going further in our design. It has a 2 cascade. One of them admittance impedance control for human-robot interaction. Another one, we have a sliding mode controller that it is the new design that is joined to the impedance controller. In this case, the impedance control has the best nonlinear controller for remove the uncertainty. Because we are this impedance control for the human-robot interaction uncertainty, a sliding mode controller for uncertainty on the exoskeleton. Because we have an identification system for the robot, and this identification should be removed because it is not accurate. We have to remove the uncertainty. In the low-level control, the outcome is the torque. In the low-level controller, we use the current control or the simple torque control that it can be done. And the first model that used for the INS is a position control, but we change it. We are focusing on the torque control or current control for the low level because we changed the high-level controller as well. Okay, it is our presentation and work and the contribution of the University of Kent.
My presentation will be just short. Do I need this one or can you just hear me? Oh, then I will. Just one time. Okay, I will be short. I'm Noël Keizers, professor at the Sint-Maarschiniek, and we are the clinical partner in this project. And what we will do is the usability of the validated functional prototype of the motion, and what would rather call it the INES, for children with CP in the clinic. So we are at a stage here at the Unia, and they developed a really wonderful exoskeleton, but it has to go to the clinic, which is in this case our Sint-Maarschiniek. We have some experience with exoskeletons, and it seems to be fine. I mean, it's just a distance of about 200, 300 kilometers. Takes some time to drive to here. But I mean, it's not enough to just take the exoskeleton towards the clinical hospital, because there is, first of all, a medical ethics committee. And you think, okay, maybe not so nice people, but they're really nice. They will help you. But they have also kind of to deal with the medical device regulation. And that medical device regulation changed in the last 2 years. And when some things change, nobody knows exactly what they have to do. And it was also the same for this medical device regulations. But what we always know is if there is a device, then you have to fill in forms. And filling in forms, that's what we still are doing. Brenda takes most of the part, and from here Enzo are filling in many forms, and they make small steps and steps, but it looks like there is light at the horizon, so it will be fine. But we are not there yet, and oh, this is just not the right slide. Maybe I can just change it. Disappear this one. And then come back. So what will we do? We will test the users and the tasks. And users is not only the users of the children, but it's also the physical therapist. The physical therapist will have to work with the exoskeleton, which is very important because you cannot give just an exoskeleton to a patient or a child and just walk away. So include those, and they both have to be a team to get the best out of such a system. And what task will we test? First of all, it's donning and doffing. And donning means doing it on, and doffing, doing it off. And if it will take you, for example, 20 minutes to put on your shoes, you don't like to put on your shoes. And it will be same for an exoskeleton. So it has to be fast, quick. And what we learned from most of our patients, they say, okay, within 5 minutes, then it's fine. So we'll focus on that. And then the other ones is the basic, general activities we do in daily life. To get an exoskeleton on your body doing standing will be quite difficult. So we would start with sitting, and then if we want to stand and walk, of course, we have to transfer from sitting to standing, which is one of the first tasks. The other one is also if you were to return from standing to sitting, and of course, standing with an exoskeleton without using, for example, crutches. And the most important one is walking. How will we do that? Start with, indeed, also the small adults. We are in the Netherlands, they might be a little bit taller than in France, but we will find some of those small adults. Then the next step will be to typical developing children. And then hopefully in the end, we will test like 8 children with CP. And if we manage to do that, then we will be really happy. And I think the project also. So this is just only my part of the presentation. And then I will come back at the next one, but because we were involved to that. But I forgot what I just took away from the slide. So I have to put control. Oh, that's a different one. Yeah. We also have to kind of test the usability of the system. And that's what we do with the system usability. And it's part of what we also did. And you have to ask children. So you cannot ask them in English. They prefer to speak Dutch if we do the test in Dutch. So that's why we also translated the system usability skill to a Dutch version. So we can interview those children after they have done the test. All right. Next one, I would say.
So now the last technical development, but not the least, the garment. Sorry, but we are very late.
Yeah.
right. Hello. I will try to go a bit fast because I think we're a bit behind schedule. Oops. Okay. So smart garment development. So the smart garment is one of the last modules in the Motion project, and it was made possible by, and I don't know why the screen is not fully showing, but made possible by several partners in the project who are all present here. Actually, I want to start at the end, or let's say where we are now. So the smart garment has actually two parts. We have the material part and then let's say a software part or an algorithm part. Noel will talk more about the last part. I will talk or focus on the materials. And this is where we are at now. So we have a smart garment with several sensors included, which can be connected to an electronic board and also has some front-end application that can read out the data of the sensors on a computer. Unfortunately, we haven't been able to test it completely yet because we have had some delays, but that's hopefully still feasible in the next few months. But what we want to do with the smart garment is actually doing some kind of stress measurement or stress detection during a therapy with the children. When I talk about stress, it's not necessarily mental stress, but also physical stress. So if the effort that they have to do is too much or not, we want to be able to detect this. And we set out to do this based on 4 physiological parameters. So the heart rate, the respiration rate, the body heat flux, and the galvanic skin response. And for each of these parameters, we developed a sensor for that. And I'm just going to go through the different sensors one by one. So start with the ECG sensor that was developed at Centexbel, where I'm one of the researchers. So the ECG sensor is basically, we made 2 cotton substrates with a silver-plated polyester yarn embroidered into it, put a clip-on button on it to have a connection that can go to the electronic board, and then use some kind of medical-grade adhesive to adhere the electrodes to the skin. We compared this signal that we get to the captive system, which is kind of a reference or standard that can be used to compare. And as you see, the signal is quite good, quite comparable. For the respiration sensor, we actually embroidered copper wires on an elastic fabric. So you can see it in the demonstration downstairs. It's a quite elastic fabric with either 2 or 4 rows. So here you can see 2 rows. In this example or this picture, it's maybe not so clear. There are 4 rows of copper wire. When you extend it, the signal changes. So it's kind of a self-inductance signal, and with elongation results in a change of the frequency of the oscillation in your self-inductance. It's quite technical, but you can measure the respiration with that. We put Velcros to fix the belt completely around the thorax, and we also need to put some kind of encapsulation on this part, so where you have the connection to the electronic board, to ensure washability of the sensor. So we put with a low pressure molding some kind of polyamide encapsulation around it. And again, we compared it to the respiration sensor of the captive system. You can see that there is some difference in the signal, mostly in terms of amplitude, but let's say frequency is quite similar. So for respiration rate, it's quite fine. Then the heat flux sensor, okay. This was developed by Junia here, and it's based on the principle of the Seebeck effect. So which actually, the effect, it's an effect that when you have a temperature difference over certain materials, you can actually measure a voltage out of it. So you need, as I understand it well, 2 metals for that. And so what they did was they used constantan, which is a copper-nickel alloy, and copper to have these 2 metals and incorporated them into a textile substrate. So they wove a constantan wire in between the polyester yarns of the textile, and then did some kind of local masking of the constantan and did copper deposition on top of it, and were able to measure heat flux. So you actually get just a voltage as an output, and was then compared to the Captec, which is a different standard here used. And as you can see in the slides below, you can also see it in the signal here. The signal is quite comparable, and the let's say the sensitivity is also quite in the same order of magnitude. So that's very good. What they did some simulations on adults for this sensor. They gave them some mental tasks. They also put a VR, also put them into some kind of VR test, which I understand will also be possible during the demonstration here. So if you want to do that, please go see it. And also some sports testing. And you can see if you compare the blue line, which is the textile heat flux sensor, and the green line, which is the CapTech reference, sorry, it's quite comparable, which is, again, a good thing. And if we can go to the next slide. Yeah, then we have the last sensor, which is the GSR sensor. So the galvanic skin response is actually a measure of the skin conductance. So it's a response that your body gives to an event-related experience, so when you're scared or when you're surprised by something, or by tonic stimuli when you have to do a mental task or when you have to do a physical task. The GSR is typically quantified, so you can see, let's say, a response signal here is typically quantified by its latency toward compared to the stimulus, its rise time, and then also its amplitude. This sensor has been developed by Kinetic Analysis, and I don't know why. Yeah, and was tested on 2 locations to check what the best position for this was. First position that we thought of was the shoulder, but eventually we decided to put it on the wrist because it gave a better signal. Of course, if you put it on the wrist, you cannot incorporate it into the garment, so we just developed some kind of wrist strap that you can see here. Also, you can see it in the demonstration part. And then we also put an arm sleeve around it to have some kind of cable management, because if you have a cable that is going from your wrist towards the electronic board, it's probably going to be in the way. So if you put an arm sleeve around it, it should be fine. So these are the 4 sensors. Kinetic Analysis also developed the front-end application to read out the data from these sensors. And this is a screen capture from that. So you can see 4 graphs for each, so 1 graph for each sensor. You have a status box, you have a box where you can submit some notes, the Bluetooth connection bar, and then some things to just start your measurement or stop your measurement. I think there is a screen capture of this that we will be able to show during the demonstration. So if you want to see this in live action, please come and check it out. And now I will give the words to Noel and maybe also Victor, I think, to talk about the algorithm. Oh, yeah. Followers.
It's not only a duo presentation, but it will be a triple presentation. Because I'm presenting on behalf of the Semacnic, but also from CAA with Victor and Andrea, and Victor will follow me. And from the Semacnic, I forgot to mention the last presentation, Carmen Ensing. She's online, so she was involved in the system usability skill. But for the stress measurements, most credits go to Rosanne Kuipers and Brenda Groen again. I mean, I'm only presenting here, but I didn't do that much, I would say. We also have Peter Jongerius, who is involved. He's a rehabilitation physician. We talked already about stress, but why would we measure stress? And that's actually kind of, we use all kind of technologies in our rehabilitation center, and such as exoskeletons, and they are not always without risk. And one of the most important risks is discomfort, because you can imagine that if you have some additional pressure on your skin, you get pressure points, and that's not really nice. So children might develop some fear of this kind of technology. And you can say that, but some children cannot express themselves quite good. So it would be really, really easy or better if we could assess this discomfort with just devices. And that's what we did in this, this part. So Semacnic designed the protocol, and we also performed the measurements. And then CA had to do the really hard stuff with the artificial intelligence, and they had to estimate the level of stress. So discomfort, I talked already, or I mentioned already, the medical ethical committee. And if you send something towards the medical ethical committee, they have a rule that not more than 25% of your subjects in your study is allowed to have stress. So it becomes quite complicated when you want to induce stress in all the participants. But we managed to deal with that, and they finally gave us approval. So what did we do? We had first stage 6 typical developing children, subsequently another 9 typical developing children, and we tested them in 3 conditions. First one is fear of height, and we used Ritchie's plank, and I think you can also feel that kind of what's happening here at the demos. We also had a row bridge, which is on the grill, which is a treadmill with unexpected movement. So the treadmill moves suddenly sidewards, kind of perturbations. And the last one that is walking with a kind of an annoying exoskeleton. We call it an annoying exoskeleton because it was not aligned on the axis of a knee joint axis in this case. Yeah, we also asked, of course, what the perceived stress was, and actually those 2, they didn't induce that much of stress, so we mainly focused on the fear of height of the Ritchie's plank. And the conditions were first, of course, no stress, and then the stress was induced. And Stijn already mentioned it, we used the captive platform with several sensors in it, and those sensors measure the ECG, the galvanic response on the fingers, respiration belt, accelerometer and thermometer. And of course, we also have to know what the perceived stress was by the children. So they indicated that by the VAS. And most children had at least a VAS of 5 or more at the Ritchie's plank. Whereas for the other conditions, they might have like 1 or 2, which was only, minimal amount of stress. And now I would like to hand over to Victor, because he will be dealing with the data.
Okay, so at CA, we developed a stress detection model, so using the data recorded by Sint Maarten's clinic. So as Noel said, we only focused on the Ritchie's plank data because the other task was not really stressful for the children. And so since the exact relationship between stress and physiological features is not known, we have to estimate this relationship by using supervised machine learning approach. So with machine learning, we can separate stress from non-stress. And so we use the data coming from the 2 measurement campaigns. So for the first campaigns was the training set. So these data were used to train the model and to select the best one. And the second campaign was used as the test set. So the test set is used to evaluate the final performances of the model. So for the machine learning methodology, we have a lot of physiological signals, so ECG, galvanic skin response, respiration, and so on. So with these signals, we have to pre-process them. So we clean them with filtering techniques. And for example, for ECG that you can see here, we transform ECG signals into interbit intervals signals, or IBI. IBI is just the time difference between 2 successive peaks of the ECG and can be related to beats per minute for the heart rate. So from all the preprocessed signals, we can compute some features. So we compute, for example, for IBI statistical features such as the mean, the median, or the standard deviation. And we do that for each sensor. And in total, we have almost 30 features that have been computed. One of the important steps once we have computed the features is to calibrate them, because each individual has its own physiological characteristic, different heart rate, skin temperature, and so on. We have to remove this variability, and we did so by removing the median of the feature during a reference task, so a baseline task during which the children were just standing still without VR equipment. And so with this calibration, we remove the variability, and then we can work on these calibrated features to test every combination of 1, 2, or 3 features, and to test also different machine learning models. So since we have very few data, we couldn't work with very complex models such as deep learning models. So we only used very simple models such as logistic regression, linear regression, and so on. And finally, to select the best model and to evaluate the performances on the training set, we use the leave one subject out cross-validation strategy, or LOSO. So for LOSO, basically, it's just to have one subject that will be used to evaluate the model, while the others are used to train it. And then we iterate over all the subjects. So here you can have an example with this figure. And finally, for the results, so on the data from 2021, so the training set, the best model was a linear regression model with a threshold of 0.5 to transform the continuous output into a binary variable. And the two most relevant features were IBI mean, so which measures the mean out rate, and the PNN50 of IBI, which is a feature that measures the variability of the out rate. And so on the training set with the LOSO strategy, we have a performance of about 92%, which is very good, but with an uncertainty of almost 9%. So the uncertainty is quite high because we have only a few data, just a small number of samples. But the important metrics is when we test the trained model on the test set, so we can see how the model can generate on a new and unseen data. And on the test set, the performance is about 84%, which is very good and shows that the model has a good generalization capability. So for the next step, we only use captive platform to measure the signals, and one of the next steps would be to combine this model with the smart garment and its own sensors. We can then also add CP children in the database because so far only typically designed children were recorded for the database. And finally, we can improve the model performances in working situations because since our model is working only with out rate, it can be tricked by working situations and it can classify walking as a stressful task, whereas it is not stressful. So maybe you can improve the model to make it more robust to working tasks using, for example, features from accelerometer. So we have already begun to work on this topic, but we don't have final results. Thank you. If you have any question, don't hesitate. It's classification. We have a binary variable 0 or 1, stress or no stress.
So for the question, I suggest to ask the question in the hall during the demonstration because we are very late. And for the person on Teams, there will be, I think, an live movie. Mince. So if you wait a minute, you can, or 2 minutes, we will have a movie directly on the screen, on your screen. So now we can go downstairs, and see the different demonstration before the lunch. No, demo. On lunch after demo, of course.
Ouais. T'as géré ton screen?
Hello.
Any plugs? No, I was thinking of a plug, so where I can put them?
You want to put your
Yes.
laptop or your phone?
It's the mobile, yeah.
For the mobile, you got a power
Up
bank.
there on the floor. I've got a that. I'm Greek. No, sorry.
It's a red wine. So. So now. Attends, no, no, I be. Edwin, do you hear me? Par contre, I can't hear
Yes,
you.
I hear you. Yeah, I hear you. Can you hear me?
Can you speak or not? I can't hear you.
I was speaking. Can you hear me?
No.
Oh, that's a bad thing. I will check.
I can hear you, Edwin.
Yeah, you can.
Yeah.
Okay.
No.
So then it's not on my side.
Try. Toi another thing, haut-parleur. Can you speak now?
Yeah, I can always speak a bit
Non.
if you want.
Ça c'est que ça marche
Not
pas.
yet.
And now?
Yes, I will try again. Can you hear me?
We hear you,
Yes. It's distant or it's good?
but the problem is I have. It's only with the sound of my laptop. Try to. And now you can speak?
Yes. Can you hear me?
It's okay. It's great. We hear you with in the room.
Okay,
So,
nice.
I stopped the share of the screen. The problem is that today the first speaker is sick. So if you can start, it's okay. No?
Yes, that would be fine. There is one thing. I'm not sure, like, is Friedel in Lille or she's also online?
No, there's a lot of person in Lille and also online too. There's an hybrid conference.
But Friedel de Grote, will she be online?
No.
She's there with you.
Yes.
Oh, that's nice. Yeah. Now, to be honest, the unfortunate thing is that I was planning to contact her to kind of discuss what each of us would be presenting. But in the end, I forgot, and I also maybe Noel already told you, but I kind of like, as I didn't get the invitation, I forgot that I had to present today, so that's why I didn't contact Friedel yet. But seeing the title of her presentation, I guess there was some overlap in things that we wanted to present. So that's kind of unfortunate. But now I would like to propose, but instead of seeing overlap, it's of course also an opportunity to see a perfect match, right? So I will kindly introduce the topic of balance controllers for ankle exoskeletons. And I will take a bit more time maybe, but then I leave the stuff that we did together, I will leave to Friedel to present. Would that be okay to you?
Is it okay for you, Frieder? It's okay? It's okay? Yes, it's okay.
Okay, nice.
So we can start now the presentation by expert. It's okay, we see your screen.
Yes, you can see my screen well.
Yes, yes.
Okay. Now, hopefully, sorry for this. For the chaotic start maybe, but I think it in the end it will be a nice fit, and I can imagine that we should manage to make it a nice story together. Is that? I'm happy. I'm fine to go.
Okay, 1 second.
Yeah.
Oh, it's okay. You can start.
Oh, okay. Now, thanks for inviting me. My name is Edwin van Asseldonk, and I'm an associate professor at the Department of Biomechanical Engineering at the University of Twente. And in the next few minutes, I would like to tell you something about the research that we are doing in using exoskeletons to support balance control in healthy persons and eventually in persons with spinal cord injury. Now, as you know, exoskeletons have been around for quite a bit, and also mostly have been used so far to support totally paralyzed patients with a spinal cord injury in walking again. But a part of giving support to totally paralyzed patients, you can also use these exoskeletons to provide support to people with an incomplete lesion. And actually, that's something that we would like to do, to use these devices to increase the axis radius of these people so that they can walk for longer distances with less metabolic cost and with increased stability. So we would really like that these devices not only decrease the metabolic cost, but also help these patients in maintaining stability and counteracting perturbations. Now, in this video, you can see the ankle-knee exoskeleton, the Symmetron ankle-knee exoskeleton that we previously developed, and that is being worn here by a patient with an incomplete lesion. And you can see that this patient can walk quite nicely with it, right? Different terrains, different, like even going outside, and all with partial support of this exoskeleton. But at this moment, if this subject would be given a push, the exoskeleton wouldn't be able to detect this push and or assist this patient in restoring his balance. And that's something that we would like to add to the control of this exoskeleton, such that it would be possible. Now here we take the approach that we first try to study human balance responses to perturbations, and try to understand how we do it, which strategies we use, try to model this, and then incorporate it in the control of exoskeletons. So previous research that we did is having subjects walking on a treadmill, and then we applied different kind of pushes. So we pushed them forward with different magnitudes, and we pulled them backwards with different magnitudes. And then we studied all kinds of parameters, among which the ankle torque that was being exerted to keep in balance. And what we saw is that like this ankle torque showed a clear modulation with respect, regarding the response that it was showing, with regard to the perturbation magnitude that you were pushing. So larger pushes to the front resulted in a large increase of the plantar flexion, while pulls to the back resulted in larger and larger dorsal flexion torques. Now, we wanted to try to mimic this behavior in the control of our exoskeletons, because we thought, okay, if the exoskeleton would show this behavior, then they are actually, then the exoskeleton works in synchrony with what the human would do, and that would potentially result in an improved balance response. Here we took kind of two approaches. First, we took the heuristic approach, in which we tried to do this in a simple way. So we took these responses and we just tried to mimic them. And then we took the more advanced approach, that's being called the neuromuscular approach. And that is work that we did together with Maarten Afschrift and also Friedel de Grote from KU Leuven. So I will today present this part, and we'll leave this part over to Friedel. But the concept is mainly, it's very similar, but the model that is being used is different. So what generally is being done is we have the human, or we have a controller, so to say. The exoskeleton controller applies ankle torques to the human. We record this response. We sense how the center of mass is changing, and based on these center of mass movements, we calculate an ankle torque that is being exerted to counteract the perturbations. Now, so the whole thing is that we would like to mimic this kind of behavior. So this was work that has been done over the last years by Christina Bayon. What she did is she had subjects walking with the ankle exoskeleton and with a pusher connected to the pelvis. And this pusher was either pushing forward or pulling backwards. Then we measured the center of mass movements, approximated by the pelvis movements. We tried to detect whether these pelvis movements would deviate from a normal pattern. So like we would estimate like how a normal center of mass velocity movement would look like. And we would try to detect where it deviates. If it would deviate, we would apply a torque. And the larger the deviation, the larger the torque that will be applied. Right, so we would detect, so this is the normal pattern. This is the pattern or the center of mass velocity if you would be perturbed. And what we would do in this kind of simple heuristic controller is that as soon as this deviation was detected, we will apply a certain gain to it, and that will result in a plantar flexion torque, helping the subject to recover balance. So what we try to do first, like eventually we would like to apply these controllers in patients with spinal cord injury, but for now we could only do it in healthy subjects, or the first step would be to do it in healthy subjects. And what we would try to achieve there is a reduction in their own muscular effort, right? So if our exoskeleton would be, or if our controllers would be effective, then the subject has to do less and can reduce its EMG activity while keeping the same balance control performance, right? So that's, we were thinking that we wouldn't improve the balance control performance. So these are the how the experiments are looking like. So you see the whole exoskeleton setup. You see here that they are connected. And I think in the next step, the person is being pushed forward, and you will see that an additional plantar flexion you see is being generated that helps the subject recover balance. Right, so here you see everything working together. So what we did is we evaluated this controller, or like we evaluated 3 different modes. Either the exoskeleton was not providing any assistance, the exoskeleton was providing assistance, and we also applied the same pushes without any exo. We did this in 10 healthy subjects, being perturbed at 2 different instances, so at the start of the double stance phase or at single stance, and with different amplitudes, either a low amplitude or a higher amplitude push. What we saw is actually what we hope to see. So here you see the center of mass velocity profile, you can clearly see that the center of mass velocity is being perturbed, right? So there is a clear deviation, and in response to that deviation, we saw an increase of the torque. If we provided a larger push, you would see a larger deviation of the center of mass velocity, and as we programmed it as such, we would also see a larger change, or like a larger assistance torque. So now the question, so apparently the controller was working as it should. So the question was, would this also result in a reduction of these EMG activities? And that's exactly what we saw, right? So if you look at these patterns, for me, it's a bit small, but like you see that these are the without exo conditions. But if you look at the without assistance and with assistance conditions, you can see a clear drop in this EMG activity when the exo was providing assistance. All right, so that's also what you see here for the other muscle, or for the other instant of the perturbations. So overall, what we saw is we saw a reduction of the EMG activity as we hoped for, while we also checked all the balance parameters like step or like foot positioning, step length, step width, center of mass position, and none of these parameters changed significantly. So there was no change in the balance response, but humans were generating less EMG activity, showing that our balance controllers were effective in supporting them. Now it's actually the next part, and I think I would like to give the word here to Friedel, because otherwise I would, we would say in the Netherlands, het gras voor haar voeten wegmaaien. But I'm not sure what is the correct translation in English for that. Okay. Would that fit for you, Friedel?
Thank you, Edwin.
Yeah, if there are any questions, of course, I'm happy to answer them now.
You have some question? Yes, there's one question. I try. How do we define muscular effort?
Oh, it's really based on EMG activity. So we integrated the EMG activity over a certain interval, and that was what we called muscular effort.
Okay. So, can you stop sharing your screen? See, there's another question from Louis Martinelli.
Hi there, thank you, Edwin. As a physio, just wondering, when you started this, did you look at, or did you think, or for future studies, did you think that look into toe clearance? Because some patients we see when they trip, obviously it's not just a loss of balance, it may be because their foot's caught, and how you then suddenly, if you've caught your foot, like caught your toe, how do you then take a higher step? I imagine that's very difficult to try and...
Yeah. So that's a nice question. Thank you. Of course, tripping is of course also nice to, or like something that you could prevent. The most straightforward approach would be to always make sure that you have sufficient dorsal flexion, right? And that's something that you could also provide. But really monitoring, like estimating where your toes are with respect to the ground, it is still very challenging, I guess. Maybe by incorporating some cameras that could be possible. But if you would like to indeed have a hiring strategy or something like that, you at least also need ankle and or hip activation, right? So if you have a full exo, that is certainly possible. But yeah, then you would require different controllers.
Thank you.
Okay. No other question? No. I have a question. So you measure the center of mass or the center of pressure?
Center of mass. That is so we measure, or like we measure the pelvis position, and we kind of assume that your center of mass is within the pelvis position. It's also important because in the end we try, we actuate the ankles, right? So in the end, your center of pressure would exactly, would be a representation of the ankle torque that you are exerting together, the human and exoskeleton together. So you kind of need to have your center of mass here. And that's something that I didn't point out here, but like, of course, it's kind of now that we have this controlled setup where people walk on a treadmill, and that we kind of need, register a well-defined push. But one of the challenges, of course, is to transfer these kind of controllers to a real environment. And then you would, of course, need more, mobile sensors or wearable sensors. So maybe IMU sensors to continuously measure your center of mass motions. You need to have probably more advanced algorithms to detect whether your balance is being perturbed and whether an action is required. So there's still quite some work to do here. So as I see it, these are the first steps that we are making in this field. And it is nice that we can support balance in these controlled conditions, but I think there's still lots of work to do to also get it to work over ground, and then also in patients, right? So that's another challenge.
Okay, thank you. So now I think Frieder will speak.
Yeah, I will attend for a bit, but unfortunately also have to leave. But Frieder, good luck, and hope you will have a nice and good meeting together. Thanks for having me.
Thank you, Edwin. So I will share the screen. Okay, and now I don't know, but if you use the microphone, maybe I have to do. No. Okay. Now.
Okay, so I'm Friedel de Grote from KU Leuven. Thank you for the opportunity to present some of our research in the design of ankle-foot exoskeleton controllers here. And Edwin is right. I am going to talk about how exoskeletons control or can also support balance. So a lot of the focus in exoskeleton design has been on efficiency, with impressive results in reducing metabolic cost, but stability is important as well. And I was really happy to hear, like in the testimonies, the parents say that like stability is important. So we decided to use a biomimetic approach to design a controller for an exoskeleton that supports balance. And so to do so, we answered 3 questions. First, we looked at how humans control balance during walking. Then we evaluated whether we can model the human balance control strategy. And then we evaluated whether implementing this model on a bilateral ankle-foot exoskeleton improved balance control. And for this last part, we collaborated with the people from the University of Twente, and that's the same setup as Edwin was showing you. So how do humans control balance? One way, like there is 2 main strategies, and one way to control balance is to adjust where you put your foot on the ground when you get perturbed. And these are 2 graphs from Vlutters and colleagues that show that there is a correlation between foot placement and center of mass velocity. And here you see these correlations in the mediolateral and anterior posterior directions. And you see that the correlation is stronger in the mediolateral direction. And that is because there is a second strategy that is the ankle or center of pressure strategy. And you can also restore balance before your swing foot hits the ground by adjusting the center of pressure under your foot. And you can do so by modulating your ankle torque. And in standing balance, we know that joint and muscle torques can be explained by center of mass kinematics feedback. But we did not yet know whether that was also true for walking. And so taking inspiration from standing balance research, we explored the relation between center of mass kinematics and ankle torques across data sets. So we had 3 data sets, a data set of with perturbations from discrete pelvis pushes and pulls. So that was collected in Twente and shared. Then we had a data set with discrete treadmill accelerations and decelerations that we collected ourselves. And then we had also another open source data set with continuous treadmill speed perturbations. And in each of those data sets, we looked at the relation between the center of mass position and velocity 150 milliseconds after perturbation onset, and then the ankle or the changes in ankle torque 100 milliseconds later. And this delay was to account for neural transmission times, as well as like electromechanical delays in activating your muscle. So what we found was that there was a relation between the change in ankle torque and the center of mass position on the left here and velocity. And what you see on the right is that we could reconstruct the change in ankle torque by center of mass, by delayed feedback from center of mass position and velocity. And this was true for the pelvis push and pull perturbations, but also for the treadmill accelerations and decelerations, as well as for the discrete perturbations. And for the discrete perturbations, you see this relation between ankle moment and center of mass position on top and center of mass velocity at the bottom for different time instances during stance. And you can see that this correlation is modulated during the stance phase and is strongest during mid-stance. So summarized, ankle torque is modulated based on perturbations in center of mass kinematics, and that seems to be like the strategy used by humans to control or to recover from a perturbation. And so our next question was, can we model the human strategy to control the ankle torque? Because if we have a model that can give us an online prediction of the human ankle torque, we can use that model to control an exoskeleton. So that is what we investigated next. And so we started from an existing reflex model. So this is the model of Geyer and Her. And in this model, the ankle torque during unperturbed walking is modeled as feedback from muscle force and muscle length. And I think the strength of this model is really that you can estimate the ankle torque with like only the joint angle as an input. And the other input you need is whether the foot is in stance or in swing. So you need very little inputs that you have to collect online to estimate ankle torque. But based on like the experimental observations I just presented, we extended this model with feedback from center of mass kinematics. And then we evaluated how well the original model and the extended model captured the human ankle torque during perturbed walking. And so this is the graph that Edwin also showed. Like if you do pelvis push perturbation, like you get a decrease in ankle torque, and that's in blue here. If you do pelvis the pull gives you a decrease, the push gives you an increase in ankle torque, and this increase is here in red. And so then we estimated model parameters by fitting the modeled and the experimental joint torques. And what we found was that the original reflex model did not capture like the modulation of the ankle torque with perturbations, whereas the reflex model extended with center of mass feedback could capture the modulation of the ankle torque with perturbations. Okay, sorry, I should have used these. So a reflex model extended with center of mass feedback captures human ankle torques. And so the next thing we then did was we evaluated whether implementing this model on a bilateral ankle exoskeleton improved balance control. And to this aim, we reached out to Edwin van Asseldonk and Herman van der Kooi in Twente because they have like the symbiotic lower limb or ankle exoskeleton. So the controller required 3 inputs. That was like the center of mass velocity, which we estimated from a marker on the pelvis, the ground reaction force to know whether we were in stance or in swing, and the ankle angle, which we got from the exoskeleton encoders. And based on those inputs, we could, with our model, compute a torque, and then we provided 30% of the model torque as support to healthy subjects. And so balance assistance reduced muscle activity. And if we start with a push perturbation, so look at the top left graph. In the top left graph, you see example muscle activity in black in unperturbed walking. And then we compared our novel controller with two existing controllers. That is a minimal impedance controller that provided 0 torque. And then like a controller based on the original reflex model. And so here you see the muscle activity for the 3 controllers, in gray for the minimal impedance controller, in green for the original model, and in red for like the extended model. And you see that the novel controller resulted in EMGs that were closest to the unperturbed condition. And so this was true also across subjects in this experiment. And then if you do pull perturbation, it is like your tibialis anterior that goes on. And also here, our novel controller reduced EMG with respect to existing controllers. And again, this was true across subjects. We also looked at center of mass perturbations, and this is what you see here. There was a statistically significant reduction in center of mass displacement for both push and pull perturbations, but for push perturbations, it was really small, whereas for pull perturbations, it might have been a little bit more meaningful. So in conclusion, balance support decreased both muscle activity and pelvis displacement in perturbed walking. And so then I want to use the last few minutes of my presentation to talk a bit about ongoing research in computer-aided design of orthosis that we are doing. And so a few years back, we developed a simulation framework. And so what you see here is a simulation of walking that was generated without using any movement data. So this simulation was generated based on a musculoskeletal model by minimizing or by solving for activations, muscle activations that minimized a movement-related cost. And so we only imposed task constraints. And for steady-state walking, the task constraints were to move forward at a given average speed and to have a periodic gait pattern. So every step resembles the previous step. And so I think the power of such simulations is that we can now change something in the musculoskeletal model and evaluate the effect on the gait pattern. So for example, we can introduce weakness in the hip muscles and then evaluate how the gait pattern changes. And so our model predicts that with hip muscle weakness, you get a compensated Trendelenburg gait with hip circumduction and trunk sway, which has also been observed in patients. And also we can use this to look at the effect of a device. And in this example, you see the simulated gait pattern when we replace the lower limb or the by a prosthesis. And you see that the model predicted ankle torques that resembled ankle torques that were measured in patients. So the next question is really like, can we use a simulation platform to simulate the effect of an ankle foot orthosis? Because if that would be true, we could like simulate the effect of a whole series of orthosis designs on the gait pattern and select a design with the highest potential to like improve the gait of like a patient. So that's kind of our dream. But this requires that we first evaluate whether our simulation framework really captures the effect of AFO use or exoskeleton use. And we started doing this evaluation in healthy subjects. And so we first wanted to evaluate whether we can simulate the effect of an exoskeleton. And to this end, we are collaborating with Steve Collins and team. And so the way we work is they provide us information about the test subject and the exoskeleton, including the assistance profile. We generate simulations. We then share the outcomes. We receive the experimental data and we can compare them for validation. We propose improvements to our models, and then we'll iterate this procedure. This is ongoing work, so we only did a first iteration. So we simulated a gait of a healthy subject walking without the exoskeleton, with the exoskeleton in passive mode, so like not providing any torque, and with an active exoskeleton. So like our predictions of the kinematics or changes in kinematics did not completely agree with the observations. So first, like the test subject did not change stride frequency in the different conditions, whereas our simulations predicted a decrease in stride frequency when wearing the passive and active exoskeleton. Our simulations did not predict any change in kinematics or very small changes in kinematics when wearing the passive exoskeleton, which was in agreement with the experimental data, but they predicted a change in kinematics when wearing the active exoskeleton that we did not observe experimentally. And then if you looked at muscle activity, our simulations captured the big decrease in soleus activity with the active exoskeleton, yet the activation patterns somewhat differ. Our simulations were pretty bad at capturing the increase in metabolic cost in gray here that we measured, but they did a better job, in predicting the decrease in metabolic cost with the active exoskeleton. So we decided to take a step back, and we looked at, we tested or evaluated whether we could capture the effect of adding mass to the leg. And so we mimicked experiments by Browning et al., who added mass to the foot, tibia, femur, and pelvis. And to our surprise, our simulations captured the observed differences in stride frequency due to adding mass. And so this contradicts with what we found with the passive exoskeleton, which you could also consider as adding mass. And so we really have to look in more test subjects, like what's happening with this frequency. We then also looked at the effects of adding mass on the metabolic cost. And also here we found that we underestimate the increase in metabolic cost due to adding mass. So this is in agreement with what we found for the passive exoskeleton. And this probes improvements in the model. At the same time, Miriam started to evaluate whether our simulations captured the effect of wearing passive AFOs on the gait pattern in healthy subjects. What we found was that the simulations captured the direction of the change, but not the amplitude of the change in the ankle angle. And so as many of the discrepancies occurred either in the ankle or due to adding mass distally, we are now reconsidering how we model the foot in our simulations. But that story will be for another occasion. I just want to finish with acknowledging the people who did most of the work that I showed here, as well as my other team members and my collaborators. Thank you. And of course, I'm happy to take questions. Yes.
Focus on the ankle. Exoskeleton. You see other opportunities to have a less bony so and also fit in balance. So maybe all the guns or
That's a good question. I'm not sure you could. Oh, honestly, I'm unsure whether you could make things less bulky. So I think there is two motivations for looking at the ankle. First is that we see this very strong response around the ankle. And then second, if you look at existing devices like AFOs, and then also like if you look at prostheses, there are available devices that have ankle activation. So we can kind of leverage that potential, because I'm not a hardware designer. And I mean, I admire all the people who do hardware design, and we've seen nice examples today, but that's not my strength. And yeah, because I think it's a really good question, but this is really, yeah, like it's like both things. Like we see this very strong response at the ankle, and we know that there is existing devices that assist the ankle, or like also in prosthesis, like ankle foot prosthesis, or that's also common. And so that makes it like I think the easiest first step, and sometimes. Yes, and so but also the thing is, like with this stepping strategy, it's way harder to assist the stepping strategy, because then you need to kind of like that has involvement of all your joints. So you almost need a full body exoskeleton to assist the hip strategy. At the other hand, I think that if you can reduce the effect of a perturbation by assisting the ankle, you might just already eliminate some cases in which you have like, you need those other strategies, because typically, so what we observe is the ankle strategy is the first thing you use. It's only when this ankle strategy is not available that you will switch to a stepping strategy. And I think that is because the ankle strategy is very fast. You don't have to wait till your next foot hits the ground. You can just instantaneously do it. But if the perturbation occurs at the end of your stance phase, of course, I mean, the ankle strategy is useful, and also in the medial lateral direction. So I think there is like, this will not solve all balance. I mean, this is not full balance control, but I think it can help.
No question on Teams? Question? No? Thank you.
You're welcome.
Next speaker is Louis Martinelli from Observation.
Yes, hello there.
Yeah, you can share your screen.
Yeah, just doing it now.
Okay.
Is that coming through?
Yeah, perfect.
Okay, just can't see if it has my entire slides up yet. Okay, is that working okay? Can everyone see that?
Yes, great.
Okay, well, thank you for inviting me. I hope you find this useful. This is, I guess, more of a practical look at how exoskeletons have been, or my experience of exoskeletons in the UK, and some of the therapist and patient feedback we have reported from it. And so I'll talk for about 10 to 15 minutes today about the exoskeletons that I've used in the adult population, and as I said, some of the feedback and some of my, I guess, just my opinion on what I've experienced. I've used exoskeletons for the last 7 to 8 years in all adults, about 4 to 5 exoskeletons, well, depending on the terminology you use, maybe 6 or 7 exoskeletons I've used with about 150 people. So hopefully this is quite a broad look at things. Just to go through what the topics I'll mention, I'll very briefly just mention how I feel we've got to this point, so the development of neurotechnology, but then specifically the different modes and types of exoskeletons that I've seen here in the UK, the reported benefits, limitations and barriers, and although I haven't used any with children, but in theory the potential uses for children from what I've seen, how I feel they could be improved in a practical sense in the upcoming years.
Okay, I found this on the web for potential uses for children from what
I'll summarize and then hopefully have a fair amount of time for any questions you may have. So I'm based in Winchester, which is about an hour from London in the south of England, and I work for a company called Hobbs Rehabilitation, and we work across the south of England. This is inpatient, outpatient and community patients, and we're an MDT, so I work with OTs, paediatric physios, neuropsychologists, and we treat people with a brain or spinal cord injury of one form or another. I think in the last 10 years since I've been working in neuro, I've seen a real explosion of when I started, the technology was limited, I guess we'd say. Still very useful, practical pieces of equipment that you may have come across before. So stand aids, some mechanical devices, and obviously electrical stimulation. And for what we can provide now, there is an explosion of sensory suits, bodyweight support machines, VR systems, exoskeletons, FES, robotics. I feel this is only going to increase. As a therapist, obviously as yourselves as researchers, it's fantastic that you're looking into all this stuff sort of for us. As a clinician, I feel students especially, it's important they're aware of technology and it's integrated into the system, because there's often lots of barriers of integrating technology into systems, not just into companies and rehab, not just exoskeletons. To talk about exoskeletons specifically now, the reason I put this slide up is, to give people a bit of a smile, I guess, but also when I get contacted by patients interested in using exoskeletons, they will have the ideas already, okay, what can this exoskeleton do for me? And I guess due to TV and science fiction, often there's this belief that they will provide possibly independent gait, functional gait, not just as in rehab terms. That's something that I'm always quite aware of, and I need to discuss with the patient before they get too involved. So as I said, in the last 7.5 years, these are the exoskeletons I've been lucky enough to use or view. And apologies if you already know these, but I'll just go through them quite quickly to basically talk about the different types, really. So there's one called Rex Bionics, as you may have come across before, which is sort of joystick-led, so potentially hands-free, potentially a functional device for in the home. I say potentially because I'll discuss this in a few moments. Then the Rewalk device, which you can see designed is different, has an internal foot plates here, used with crutches, is the most widely used in the UK. I believe there's about 40 in the UK. People that have a Rewalk exoskeleton. These are all spinal cord injuries. The Indigo, which I believe has now been taken over by Exobonic. Similar presentation, how it looks to Rewalk, but from when we've been lucky enough to have a go in it. Very sophisticated in its settings, in the way that you can increase and reduce the motor output of the various joints, the knee and the hip, to challenge or assist the patient more as needed. Again, used with crutches. In practical terms, the real benefit of this one, from my experience, is the fact it's modular and it can break up and be transported. So if I had a spinal cord injury patient who, due to their injury, wasn't going to be walking freely again, but wants to walk in a device and wants to go with their family and friends for a walk along the seafront, whatever it may be, this is a device that you can transport quite easily. So again, in theory, a good concept. And then finally, the Exobionic. This is the one I've used on a daily basis for 7 or 8 years now. And specifically designed as a rehabilitation tool. So it has high shoulder straps, so you can have a high spinal cord injury into it, or high spinal cord injury into it. External foot plates providing good support for the feet, and a variety of settings where you can change stride lengths, step height, speed of swing, and also how much, I guess, the motors are helping during the step and the stance phase of gait. So we really like this one here. We use it a lot as a gait training, but also physiological training aid. Again, so I haven't been here for the conference all day, so I don't know if we've touched on some of these, but these are often the conversations. Patients will call me up and ask about these other sort of recent advances in the last sort of, I think, 4 years, 3 to 4 years. One of the ones that hit the headlines in recent years was the team in Grenoble, who were looking at an implant and allowing this gentleman, I think he's the first person with a texture injury, so arms and legs affected, to be able to control a robotic device through his thoughts. Again, I'll discuss these in a bit more data later. Wondergraph, again, I believe that's in France as well, a company who have looked at controlling device through, again, a handhold device, and not too dissimilar to the Rex, I guess, in the idea that someone could be hands-free and using an exoskeleton. I include Exomotors by Fourier just because I believe this is quite widely used in Asia, so I haven't seen it in the UK market yet, but from my understanding, it's similar to the Rewalk, in a device that potentially allows someone with a spinal cord injury to mobilize more freely and be on their feet. We have looked at free bionics from Taiwan. I liked this one in the sense that I didn't feel it was all quite there yet, but it was about a third of the cost. And as I'll come on to in a few moments, cost is a huge issue or challenge. And to have something come into the market that was going to undercut most of the others by about 2/3 was pretty impressive. I've included the how. Going to be very lucky enough to use this with a few patients. Although it's not defined as an exoskeleton, I believe they define it as a cyborg. It works very differently. For those of you that don't know, you have electrodes on the quads or the hamstrings and the glutes, and they will pick up EMG signals and then respond to that individual's activity. So if the patient's got a very weak thigh, very weak quadricep muscle, there's a slight muscle firing there, it will pick up on this and reproduce that movement. So from a therapist's point of view, this is a fantastic feedback loop where the individual can learn to fire the right muscles at the right time to improve the right gait. So again, in theory, a fantastic tool to use to improve gait re-education. Just quite challenging, very technical. And although we're quite technically minded here, it was quite a challenge for us. And then the ExoNR, the newer version of the exobionic exoskeleton I use at the moment. Again, I'll run through these. The reported benefits are far and wide. Again, as you may well know if you looked in literature, when I was first doing this about 5 years ago, it covered almost everything. And when we see patients in the clinic with a spinal cord injury, they're not all looking to stand and walk again. Some of them have had a catastrophic injury where they're looking to manage their spasms better or manage their bladder and bowel management better. So these will cover a whole variety of things. And the ones that are outlined in red are ones that have also been shown to be improvements in self-studies or case studies that we've done in our own practice. So this is for spinal cord injury, reported improved bladder and bowel management, maintained bone density, blood pressure, psychological well-being, which is a huge aspect from what I see here in the clinic, which is quite hard to measure. Improved exercise tolerance. So as Edwin was saying earlier, people that can walk maybe 10 meters, now they can walk 20 meters or further because their efficiency of gait. Improved sleep, walking function is a massive one if you're treating patients with a stroke who maybe circumduct their leg. Reproducing really nice gait patterns in the exo, 400 or 500 steps, they tend to walk very well after it. Improved circulation. We'll get people coming in with, poor circulation in their feet, blue feet, and they stand and take a few steps and they get red and good circulation almost immediately. Reducing risk of falls, as we discussed, reducing pain, spasticity management. So as I'll talk in a moment or two, I guess with the pediatric population, if I was to compare, we've seen quite a few people here with MS who present as toe walkers, which is, again, I guess like quite a lot of the CP population. And what we've found is walking a nice gait pattern, getting a heel reference, getting weight through their joints, the tone can drop off quite nicely, quite quickly, and then their gait straight afterwards is really improved for a short period of time. So thinking forward in the future, if there are these things for the pediatric population, I imagine the spasticity management would be one of the key aspects. And then improved length and strength of muscles from being in a nicer posture. The benefits that we've found from traditional therapy, the main one is just the amount of volume and steps you can take in a session. So in the past, we may have walked in a therapy session, if you're having to assist someone who can't walk, for example, there may be 3 or 4 of you walking, aiding someone step across the gym for 10 meters, and that might take 5 or 6 minutes, and they may take about 20 steps. And now in a session, I could take 400 or 500 steps in a session with that patient with one therapist. So you get increased volume, which were, in our experience, and what there's lots of research would suggest, increased intensive therapy in a shorter period of time, you're going to get better motor function output. The technique and alignment of the walking tends to be a lot better because you control the trunk, the hip, the knee, the ankle, the shoulders, and providing that central stability tends to get better distal activity. Yes, as I mentioned, reduced staff required. This is an interesting one. From a therapist point of view, it has been noted, it reduces the strain for a therapist because the exo is doing a lot of, obviously a lot of the work. And I've done a bit of work in pediatrics years ago, so obviously therapists often bent over quite a lot. I guess the thing to pay attention to here is in the past, without an exo, I might walk a patient for 5 or 6 minutes and get tired. Now, because we can take 400 or 500 steps, we're walking them for almost an hour. So for example, we usually on a Friday have 4 patients in for an hour each. So I'm actually potentially walking for 4 hours a day with a patient with my hands in this sort of position, sort of chest height level. So in some ways it's easier on the therapist, but in others, because you're actually doing more walking, it can be more strenuous. And almost all the patients I've come across, they engage in it, they enjoy it, they like it, they're very keen. We have patients that travel, 4 patients a week that travel over an hour and a half to 2 hours to come and use the piece of equipment to use the exercise. So patients tend to be really keen on using it. What I'll briefly talk on now is the limitation of the barriers. And this is from a patient perspective. So a colleague of mine, Kirsty Cook, she, in a different centre, had a group of about 10 spinal cord injury patients, and she got these different models in, the Rex, the ReWalk, the Indigo, and the exobionic exoskeleton, and tried it with all of them and then got their feedback, and this is what they came back with. The main thing was the cost. They currently cost from between, I think, £80,000 to about £135,000. That's extremely expensive for clinics, hospitals, but especially individuals that are looking to purchase them. So as I'll speak a bit later on, it'd be fantastic if some very smart engineers out there can make them a bit cheaper. Access them is really tricky. So if you can't buy one, but you want to go and use one, obviously in the UK, there's ourselves, we can come and use or trial an exoskeleton. There's not many. I think there's only a couple of the exobionics in the UK that people can try and use. There's not access to them. How suitable are they? So the inclusion criteria is very strict for adults, and this is so that everyone's been safe. So over the years, fingers crossed, we've got a clean run. No one's had any injuries, severe injuries, skin issues from using one. That's because the inclusion criteria is very strict. So if I have a spinal cord injury patient who isn't standing yet, they can't use it. If they're not between 5'2" and 6'4", they can't use it. If they've got osteoporosis, they can't use it. If their spasms are too high, they can't use it yet. And specifically for the PEDS population, I'm assuming for the adult exoskeletons, they need to have 90 degrees at the ankle, full knee extension, and approximately sort of 10 to 15 degrees of extension. So we've been successful because we've put patients into it who are suitable. I guess the question is, if you've got patients that can't fit in these exoskeletons, what do we do there? Either the patients need to stand more and have more Botox with them maybe to get to that range, or do you design an exoskeleton that can have more leverage at the same time that may increase the injury rates once used? They're hard to get in and out of, often need an assistance of one. I think patients' perception, probably due to the marketing, they often think they may be independent in these devices, and a small population of people are, but generally speaking, you always need a spotter behind. And for example, the image on the left of the Rex, I think when it was first designed, it was looked at being an independent functional tool, but I think it's moved away from that now. It's a fantastic tool to stand in and do exercises in, but maybe in a gym setting. For example, if that lady had a spinal injury, for example, she can probably do an awful lot in her wheelchair. She can toilet, go to the cafe, get on buses, get off. With this one, for example, it will be slower than a wheelchair. Yes, you'll be standing, but people have found it's actually hard to do functional tasks in them. The difficulty to transport, apart from the Indigo, home environment isn't always suitable. So where are you going to walk with these devices? Are your doorways wide enough? Have you got enough space? So before patients purchase or look to purchase, we always try and do an assessment at home if possible. And they take a lot of practice. So I'm trained in the ReWalk exoskeleton. So if an individual's bought one and wants training into it, it can take from 10 to 40 sessions to become safe in using it, and also train your spotter behind. And that's also an added cost and time to all these. But everyone agreed they're a very good training tool. They enjoy being in them. They felt it was a very good exercise tool, as I mentioned before, not just for walking, but physiological factors such as blood pressure management and bladder and bowel management. So though I haven't used them with children, a couple of years ago I did get in a conversation with a gentleman called Tom Taverner, who at that point was based in Spain, and he worked for a company called Marzi Bionics. So this, you may all be aware of this. And we're working to try and get them over here to do some trials. So again, I haven't seen this piece of kit. It's just the only exoskeleton I know that is apparently suitable for PEDS. I believe it works between sort of 3 to 14-year-olds, depending on their height and weight. My initial questions would be, what's the inclusion criteria? Because the inclusion criteria for the adults is really strict. Is it strict for the children? And I imagine with lots of children who may be toe walkers or have difficulty with range in their hips and maybe be lordotic, do you allow them to try this? And would it support them? Or if you're performing hundreds and hundreds of steps in a not suitable pattern, you can end up getting issues. So I'd be interested to find out more. But if it's safe, I think I can imagine it have fantastic benefits, not just in a gym setting for improving someone's stride length or technique of gait, but possibly for participation. I think on the Mars Bionics website, it shows a child sort of standing and playing in its gym environment. So for some individuals who may not necessarily going to be on their feet, allowing them to be on their feet for lots of physiological and psychological benefits could be really beneficial as well. As far as costs go, in this country, patients, if they've had a spinal cord injury due to an accident, may have a medical legal claim. And some people, I think lots of the rewalk individuals have had that either fundraised or due to their medical legal claims, it's been included in. So it's almost the last slide. So my experience, in my opinion, the technology is really good and probably continue to even get even better, especially with the studies looking at the implant and moving limbs with the power of thought, and seeing what Edwin was discussing earlier, looking at it was the smaller exo, but looking at balance reactions. The technology is fantastic. From my point of view, the affordability is really poor, and therefore the availability is even poor. There isn't enough of them, and it'd be fantastic if there was a cheaper, smaller, simpler model that still allow patients to take these numbers of steps, this volume of training to get all the improvements they need. So if there was one that was better marketed in that sense. So to summarize, technology is only going to increase in the setting that I'm in, neurorehabilitation. And so it's good that the clinicians are aware. And on that point, the company I work for did set up something called the Mint Academy, which is an online training platform. So the students that come in here, I put them on it so they can have an idea of what technology is out there for neuro and what the uses may be. So it can be quite hard sometimes searching through what's appropriate and what's not. Despite all the advances, they're really expensive, and there's not many exos available to try. From what I know, there'd be great scopes used in the pediatric setting, improving children's adherence to exercise, increasing the number of steps. The quality of stepping in particular would be important to improving someone's gait. If that wasn't their goal, and just to improve their participation in things, there may be potential for that as well. But bear in mind, almost definitely with a spotter, I'd imagine. And also, not all exos are the same. So then, on that first slide, you saw the Rex is really quite different from the exobionic. So if we're looking into exoskeletons, which one are we looking for and why? And in the clinic here, it's really on what the patient wants. If the patient rings up and says, I want to use an exo, I'd say, well, why? Then we say, I really want to be outside walking with my family. Okay, so you're looking for like a multi-terrain one, more like the rewalk that's done a few marathons in its time. If they said, I want an exoskeleton that's going to improve my gait function, I'm going to be using indoor so I can then walk better when I'm not in it. Okay, you're looking for a different type of exoskeleton then, something more like the exobionic. And yes, they continue to be funded or claimed in spinal cord injury claims in this country. And I haven't done delved into research in the last couple of years or since COVID, to be honest, but there's always new case studies coming out from our clinic, but also more worldwide. When we got to see the how, there was an awful lot of evidence supporting the how's use in rehabilitation. So again, I'm confident that they're a good tool when used appropriately. And hopefully now I've left some time to have some questions. Thank you very much.
Oui, there's a question. Yes, Noel.
My question will be to robotic gait devices.
Yes.
So I didn't quite catch that. Do you mind saying that once again?
Yeah.
I will start over again. You also have robotic gait devices like the Locomod.
Yes.
How do you see the benefit of wearable exoskeletons above those robotic gait devices?
Thank you. Yeah, really interesting topic. I think a few years ago I looked at a study that was saying the pros and cons between both. In this country, or for the company I work with, we use Tyra Motion apparatus in our Bristol centre in the west of England, and that has a Lexo device. So I was quite keen to actually practice. Let's have a look at seeing the difference between a Lexo, so an end effector, and an exoskeleton. And I think for the individual, you'll come across individuals that would just benefit from one from the other. Spinal cord injury patients who may, lack extension, tend to do better in exoskeletons from my experience. And someone like who's had a stroke injury, he may have an extensor patterning but not a flexor patterning, tends to do quite well in end effectors. It's going to sound really vague. I just think the more the merrier. And I believe a hospital quite near where we live here, so Bournemouth, about half an hour from here, in the last 2 years, they've now got a Locomat. So they are being used. So broadly, can we just get people up and moving and have more of them? The issue with the Locomat is there's probably 1 or 2 in the country and people can't get to them. If we had the choice of picking, if that was a luxury, then I do like exoskeletons because you get that ground reaction force with balance and midline awareness. But the fact on a Locomat, you can take so many more steps in a period of time. You're going to have other possible physiological benefits, but maybe not the balance benefits. That'd be a fantastic world if we could pick between one or the other, if there was enough of them.
Thank you. Other question? No? I have a question.
Yes.
If you have the opportunity to buy an exoskeleton for children, do you try it?
I think that's why we're interested. I was contacting this Marzi Barnett's company last year because we have quite a few referrals. We have a big paediatrics team here, relatively big. We have about 5 or 6 clinicians who are very busy and work from lots of schools locally. And not all the time, but every few months, I'll get inquiries from children who are 3 or 4 years old, or parents of children 3 or 4 years, right up to 14-year-olds, or adults who have had cerebral palsy but may not be 5'2", looking, and that's pretty much all the adult exoskeletons. The limiting height's 5'2". So I think there's definitely a market there, and we'd love to use one. We just haven't found one in the UK accessible. And I guess the challenge would be, from my point of view, is that biomechanics. Of course, every pediatric patient's different, but the presentation of flex pattern, maybe not with full hip extension, maybe not with dorsiflexion or full knee extension, how would you then fit that person into a traditional exoskeleton? Would the exoskeleton have to be designed differently to allow for that different biomechanics?
Thank you. So, no other question? No? So we finished with the different presentation of the experts. So maybe we can conclude or make a round table if you want. Do someone tell something about the motion project? The conclusion? No? Or me, I will do it. Okay, so first of all, I will thank you all of you to be here with the high level of the different presentation we have seen today. And my conclusion is I'm sure that we have to continue the motion project because it's a very interesting project with the different exoskeleton modules on the garment. And if we manage to have more fun, it will be very great because we have a lot of progress to do for the children. So I have nothing more to add for today. Just for the member of steering committee, I will organize a steering committee before the end of January. And for the other and for the people, we can have now a convivial moment. Or maybe we can make a picture here. Yes, you can come and we have a picture with a photograph. So thank you for the person in Teams. The meeting is end, and thank you. I will send you a questionnaire after the